Hi, everyone. My name is John Tarella, and I'm going to be your tour guide today. Um, Before we begin, I want to mention that this is an activity intended for students who are in Calc BC um, and who are already familiar with the technique of doing integrals using partial fraction decomposition. If you're not familiar with how to use that technique, the logical ideas we talk about today and how the calculus relates to practical applications will probably still be interesting to you and understandable. But the actual technical math that you're going to get into in small groups is going to be tough, if not impossible, because you don't really know the underlying technique for it. So you might want to stick around, you might not. It's really up to you, depending on if you are okay with learning the math either very quickly or not being familiar with it. Um, so what we're going to talk about today is something known as the logistic population model. I have put a link in the chat that you can use to get to a Miro board that I made. It's an online whiteboard that you can view while I write on it. I could let you guys edit it, but I don't think that would be very practical with how many of you are here. So yeah, you're just going to be looking at what I'm writing. And after all this, I will send you a PDF of this that I make just from it. I just copy it as what they call a slide, and I'll send it to all of you as a PDF. I'll make it available. Anyway, so the logistic population model is a model from ecology. Again, this is a practical application of differential equations. This is not just some arcane equation that we're solving for the sake of solving it and pushing around numbers and performing algebra. This has a real pragmatic use. There are a lot of instances where things in the real world are best modeled by differential equations, because what we're saying when we model something with a differential equation is that the easiest way to describe the phenomenon is in terms of its rate. And that means in terms of how fast or slowly it progresses, as opposed to in terms of how much there is at a given time. So it's the rate of change of the thing, depending on time, how much there is, or a combination. But it's not what you'd like in a lot of cases, which is just a formula for amount as a consequence of time. You know, it's not a simple thing like if you get paid $20 an hour, money equals 20 times time. You know, it doesn't work out that nicely. Um, and because it doesn't work out that nicely for a lot of things, that means that there are differential equations that we simply cannot solve using analytical methods. You know, you can try all day to do the integral of this. I mean, it's very easy to separate. But then when you get to here, you basically got a dead end. So if that were your differential equation, you would be in, you know, in trouble if you wanted what's known as an explicit or general solution to the thing. So we would not be able to solve that using conventional integration. In the modern world, we have computers. You guys have used basic things like Euler's method to describe what a graph should look like based on initial conditions. We're also going to use a slope field generator later that allows us to see very good versions of y equals f of x graphs based on their differential equations. But what I should say is that what we have today is a model describing population that we can solve analytically. It is possible to actually separate the variables, do the integrals, and get a formula in the form y equals f of x, or in this case, p equals f of t. Population is a function of time. So what I'm going to do is I'm going to put all of you guys in breakout rooms. I'm going to separate you into 3 or 4 people apiece. And what I'd like you to discuss are a few things. I want you to talk about what would happen, and again, there's no math here initially. I want you to talk about what would happen if you had a population of wolves in a forest and there were a few different circumstances. One is if they're vastly underpopulated, so there's a ton of rabbits, not a lot of wolves, not a lot of competition for the food that's there. One is if they're slightly underpopulated, where the population could accommodate a few more wolves. One is if the population were just perfect. And the last two are if there's a little bit of overpopulation and therefore more competition between the wolves, probably not enough rabbits to feed the wolves. And the last is if there were a severe degree of overpopulation among the wolves. So I would like you guys to discuss what would happen under all those circumstances. Again, very underpopulated, slightly underpopulated, just right, and slightly overpopulated and very overpopulated. And talk about what would happen to the wolf population as time went on. Okay, and I'd wait. They would talk about things. And then we'd come back and discuss, and I'm going to try to do this, interacting with no one. Alrighty, so you guys went over this a little bit. You talked about what would happen in those particular circumstances. What do we think would happen if there were a severe degree of underpopulation? If we had a forest with, thousands of rabbits and maybe 15 wolves or something like that. Good, I agree. There would be it would be easy living for the wolves. There would not be much competition between them. There would be plenty of rabbits for everyone to eat. If you don't know, rabbits multiply very rapidly, so the rabbits would regenerate themselves fairly successfully. And there would be no inhibitions initially on how that wolf population could grow. So it would grow very rapidly because all the wolves would have plenty of food, their babies would have plenty of food, everything would be fine. If there were a slight underpopulation, one might imagine it would be the same thing, but to a lesser degree. There'd be more competition for food. There would still be ultimately enough rabbits to go around and create a net population increase, but the degree to which each wolf would just be able to readily survive would probably not be as great as if there were very little competition. What do we think would happen in the case of severe overpopulation? Yeah, exactly. If you have a ton of wolves and not that much food for them to eat, some of them are going to starve, they're going to fight over food, they're not going to be able to feed their offspring, and so there probably is going to be a general decline in the population. And again, if that's more minor, if there's just a slight overpopulation, we're going to see a smaller degree of that. We're going to encounter a situation where, yes, the wolf population is probably decreasing, but the ratio of, a little morbid here, death to birth in each generation is probably not so high. So we're probably not going to see that much of a decrease with each generation. Now, if the population is just right, which we're going to refer to as the carrying capacity here, where it's just the right amount of animals for that particular environment, one would imagine that the population would just sort of vary very minorly. Some generations do a little better than others based on weather or whatever other circumstances. But generally the population stays pretty steady at this carrying capacity, the amount that the environment is capable of holding. So now what I want you to do is quantify that a little bit more. If I were to talk about what happened here, let's say this is my carrying capacity. The situations we described are basically like this. Very overpopulated, excuse me. Slightly overpopulated over here. And then our underpopulation examples would be sort of mirror images of those. Our slight underpopulation is here, and our very underpopulation is looking something like that over here. And for something that's basically dead on with the carrying capacity, it's basically going to stay steady with some minor fluctuation going on. Our model ends up being simple, so it basically keeps the carrying capacity steady, plus it's easier to see all these things on the same graph if I leave it there. So I'm going to make it a line. So now, what I would like you guys to do is draw a slope field for the following. It's going to be dp dt equals, what did I have in my notes here? It was 2p times 3 minus p. Notice this does not depend on t, it just depends on p. And I want your x and y ranges for values to go from -1 to 5 and -1 to 5. So please go back into your groups and draw these. And what I want you to talk about is how these relate to the sketches that I just drew, how the slope field is going to sort of mimic these pictures and what scenarios they represent. I'd also like you to talk about which values of P and T, hint in which quadrants really, have no real practical value here for the model that we're trying to look at. And then when you're done with that, I'm going to post this in the chat, copy and paste. I would like you to go into this this applet. It's a little slope field applet that's really neat. It's a good thing to have around in general. And what I would like you to do is just mess around with it a bit. Try different values in place of the 2 and 3. All right, off you go, and I'll talk to you guys in 10 to 15 minutes about this. Thank you.